Okay, in this lecture we're going to be looking at NMR spectroscopy. NMR stands for nuclear magnetic resonance. Before we look into more detail about NMR spectroscopy, let's just remind ourselves about what sort of spectroscopic methods we've used in the past. So infrared we've used in the past, which determines the functional groups available within a molecule, and mass spectroscopy tells us about the molecular ion peak and the fragmentation patterns. Now, of all the different chemical techniques available to us, NMR is actually the most useful technique in terms of providing the single most important bits of information you can yield from a standalone technique without having to combine NMR with mass spec or IR. This is how a typical NMR spectrum looks like. You've got a series of different peaks, and these particular peaks listed here, for example, the methyl peak is listed as number 2, the CH2 is this one here, and CH3 is this one over here. Now each one of these different peaks actually corresponds to what we refer to as a different type of chemical environment. So in this molecule, if I just zoom in a bit here, in this particular molecule what we have is 3 different peaks, and this one is a distinctly different environment compared to this one over here, and this one is a different environment compared to this and this. Okay, so let's look now at how a typical NMR spectrum looks like. More closely resembled to real life, you have 3 different peaks for the molecule butanone. You have a scale over here which is referred to as a chemical shift. Now, just like in infrared spectroscopy, for example, you are given the actual values for the peaks. For example, if it's a hydrocarbon peak, it appears in this particular range. If it's going to be a CH type peak, it's going to be in this type of range, for example. So what we're going to do now is, first of all, look at the different types of environments, or equivalencies as we could refer to them. So in a spectrum there is one signal for each set of equivalent hydrogens. I'll be looking at a few more of these examples in a few minutes. The intensity of each signal being proportional to the number of equivalent hydrogen it represents. Again, we'll look at a few more examples of this in a second. So let's look on to this particular slide. I've got different compounds listed over here, and each of these compounds in a few seconds I'll be looking at to determine what we mean by different number of environments. So first of all, let's look at this one over here. What I'm saying for this particular molecule, and I'm sure you all recognize the fact that this is a propane molecule, and if I was to write the structural formula, I'd be writing CH3, CH2, CH3. Now, I've given the answer over here, which is saying there are 2 sets of equivalent hydrogens. What that means is this set of hydrogens over here, 2 hydrogens over here, are different to this set of hydrogens and this set of hydrogens. However, the 2 hydrogens labeled in red are chemically equivalent. And why do I say they're chemically equivalent? Because this CH3 group is the same distance apart from this CH2 compared to this CH3 being a certain distance apart from this. In other words, the neighbor of this CH3 is a CH2, and the neighbor of this CH3 is also a CH2. So that's why these 2 are the same and this is different. Let's look at the next molecule now. In this particular molecule, we have 4 different environments, and just to look into that into a bit more detail, this CH3 this time round, unlike the example over here where this CH3 is the same as this CH3 is now not the same as this CH3 over here. Let's look at why. This CH3 is next to a CHBr. Say that again. This CH3 is next to or neighboring a CHBr. This CH3, however, is not next to a CHBr. Instead, this CH3 is next to a CH2. So this CH3, because it has a different neighbor here, is different to this CH3, which has a different neighbor over here. Let's Let's move on to the CH group now. So the CH group here, or the H I should say in the CH, is very different to the H here, here, or here, because it's the only H which is bonded to a carbon which is bonded to a bromine. This H is bonded to a C which is not bonded to a bromine. Same here, this H is bonded to a C which is not bonded to a bromine. So as you can see, all four hydrogens are very, very different, so I will have four different environments. Now the point of repeatedly talking about different environments is that whatever number of environments or equivalent sets of hydrogens I'm going to have, that is the number of corresponding peaks I'll get in the NMR. For example, coming back to propane again, I would see two different peaks for propane, one peak for this set of hydrogens and one peak for this set of hydrogen over here. In this particular case, because I've got 1, 2, 3, 4 different hydrogen environments, I will actually see 4 different peaks in the NMR. Let's move on to the next one now. In this particular case, let's just try and label the different types of environments. So what I would have is, first of all, this CH3 is the only CH3 which is next to a CHBr. So this is quite unique, so it's one particular environment. Let's move on to the next one now. This CH3 is also the only CH3 which is next to a CH2. So this is unique as well. And I can keep going through this until I eventually get to a set of 5 different hydrogen environments. Now I just want to focus very briefly on this bit here, which has got 2 CH2s. Now one could argue that the CH2 here is actually the same as the CH2 here, but it's not, because this CH2 is next to a CH3 and this CH2 is only next to a CH. So again, because the neighbors are different, the actual environment is classified as different. Let's just point that out very clearly. So this one is affected by that, and that one is affected by that. So therefore they are both different. And for that reason, this molecule over here will have 1, 2, 3, 4, 5 different peaks in the NMR spectrum. And finally, let's look at this one over here now. Now, this is not that simple, because in this particular case, unlike the previous cases, this set is actually the same as this set over there, and the reason for that is they are both equal distance apart compared to the COH over here. So they're both on the same carbon atom. That's on the carbon atom here, that's on the carbon atom here, which are both connected to the OH. And if I finish off the answer now, you can see in this particular case these two are exactly the same. This hydrogen is very different compared to everything else, because it's the only hydrogen which is connected to an oxygen. And again, this CH2, the neighbor for this CH2 is CH3 on one side and all this on the other, whereas the neighbor for this CH3 is only a CH2 over here. Now, what I would like you to do, which you probably won't do right now, is to look at these molecules. I would like you to draw the displayed formulae of each of these molecules, and then based on the previous slides, which I will publish on Annotate in a few seconds, I would like you to simply determine or put different color rings around each of the individual displayed formulas that you have drawn to represent the different environments, as I've demonstrated a few minutes ago. If there is any feedback that you would like to leave for me, if you could do that on Remind right now, that would be really, really helpful. If not, we can follow up tomorrow in the actual lesson. So within a few seconds, you should see the actual slides being published on Annotate, and I'll await your feedback on Remind. Thank you.